So, it's my great pleasure to introduce Michael Abrash. Michael is famous in multiple ways. You may know him as an expert on assembly language programming and graphics programming. He's written some very well-known books in this area. You may also know him as one of the authors of Quake, one of the seminal game engines. So games, before there was Unity, which you guys are all using for your projects, there was Quake, and Michael had a major role to play there. You may also know him as a VR guy, and his latest incarnation is as chief scientist at Oculus, and he also runs the Oculus research group or lab in Redmond. And he's also been a terrific advisor for this class. So whenever I wanted to figure out, okay, who should I invite, what other speakers, obviously other than Michael, he's had great ideas and he's helped me hook up with other speakers, like he's the one who suggested Nick Whiting. He's also provided some Oculus devices for the course. So anyway, been a terrific resource for the class, and I'm excited to have him talk here.
Thank you. Wow. Being well known for assembly language is like being well known for vacuum tubing. But back in the day, that really mattered. I actually remember when I first came across a C compiler, believe it or not. It wasn't clear then what the language would be. Would it be Pascal? Would it be C? Would it be Fortran? Fortran, yes. And actually, my first video game was written in Fortran for a CPM machine. Anyway, good morning. How many of you have seen any of my talks? Uh-oh. Well, some of this will be familiar to you. So what I encourage you to do is ask questions as you go along. I have a talk prepared, I'm going to go through it, but I would really rather this be more of a discussion than me standing up here lecturing you, because it can go in lots of directions and there's so much interesting stuff about VR and AR. So anyway, I'm very happy to be here today to talk to some of the most fortunate people on the face of the earth, which would be everyone in this class. I know you've all worked hard to get to where you are, but you're also incredibly lucky because you're diving into virtual reality at the very moment when it's finally emerging after 50 years of trying. VR is truly something new under the sun. It's a fundamental shift in the way that we interact with information and computers, and it's just at the start of an exponential ramp that ultimately is going to change pretty much everything about how we live, how we work, how we play, how we interact, how we communicate. To understand why that is, I'm going to start by taking a look at the closest historical analogy to what's happening with VR, which is human-oriented computing. And as a note, by the way, most of what I'm going to talk about today applies to augmented reality and mixed reality just as well as it does to VR, but for simplicity, I'm just going to call it all VR. Human-oriented computing means computing that's designed to work symbiotically with people in order to augment human cognition, rather than requiring people to serve the needs of the computer. That's pretty much the way that all the computers that we interact with today work. Desktops, laptops, tablets, phones. But that was not always the case. 50 years ago, in fact, human-oriented computing was really nothing more than a distant vision in the minds of a handful of people, particularly JCR Licklider. So how many of you have heard of JCR Licklider? I got an almost hand up. Sadly, that is pretty typical, and yet Licklider, more than anyone, is responsible for the technology on this slide and for the way you interact with information every day. So he was called Lick, actually. Lick was a psychologist who encountered Wesley Clark's TX0 computer at MIT's Lincoln Labs in the 50s. And at the time, computers were considered basically to be big batch number crunching machines. But Licklider had a vision of how they could enhance human potential that became his life's work. So at ARPA in the 1960s, he furthered that vision by funding networking research, which he called the intergalactic network that actually led to ARPANET, which led to the internet. He also funded research on bitmap graphics and mouse-based windowing interfaces. So at the time, computers were almost entirely batch processors, driven with decks of cards and magnetic tapes, and it's actually quite possible, hard as it seems to be to believe, that they would have stayed that way without the ARPA community that Licklider planned to nurture. So I think it's really fair to say that Licklider planted the seeds of the digital world that we all live and work in today. Those seeds have been planted by the late 60s, but they were only starting to germinate. The future was starting to take shape, but elements of human-oriented computing were crude at best, and a lot of the technology needed to wait for Moore's law. So for example, the memory for a bitmap display cost $100,000. But they could project that by 1983 it would cost $35, and in fact it did. And yet no one knew what that interface, no one knew what the interface would look like. When Doug Engelbart started working on a system based on a pointing device, his first choice was a light pen. Anybody here ever used a light pen? Okay, you would take it, you put it on the screen, and it actually looks at the raster scan and tells where you are on the screen. Seems more intuitive, right? Rather than using this thing down here and looking at this pointer, you just point to what you want. His second choice was a joystick. The block of wood with a ball in it that came to be called a mouse was a late arrival and was anything but obvious. In fact, what happened was they built it and they noticed that people just kept using it. They kept preferring it. During the 1970s, Bob Taylor gathered a lot of the best and brightest computer scientists working on various parts of human-oriented computing, bringing them together at the Xerox Palo Alto Research Center, Xerox PARC, in the computer science lab. And there, they built the first true human-oriented computer, the Alto, which for the first time put together the whole package. For starters, they invented a laser printer, enabling printing of pretty much anything. But laser printers were really expensive, so if you wanted them to be useful, you needed to have a network so people could share them. So they invented Ethernet. If you really wanted to use a laser printer, you need to be able to create content. So to create content, what you needed was bitmap graphics and a mouse and a CPU dedicated to a single user so that you could actually do interactive work. And at that time, CPUs were not dedicated to single users. And on top of that, they built a windowing interface with menus and dialogues, WYSIWYG word processing and desktop publishing, and they created an object-oriented language, Smalltalk, to make it easy to prototype and design these apps. Then, as legend has it, and I bet a lot of you have heard this one, Steve Jobs and the Lisa engineers came to see the Alto in 1979, and the future of personal computing changed forever, leading to the Macintosh and Windows. So there's a direct lineage from Licklider to PARC, to the Mac, to this Mac Air that I'm showing the slides on. And the rest, as they say, is history. The course of every one of our lives has been deeply touched by Licklider's vision. In fact, I think there's a good chance that the current studies or jobs of most of you in this room wouldn't even exist if it weren't for human-oriented computing. In all the years since Licklider's vision, there hasn't been another opportunity to have as big an impact on the digital world as he has, until now. VR is very much like human-oriented computing was 50 years ago. It's a vast, unexplored territory with huge potential and no guideposts to follow. And as important as Licklider's revolution has been, I actually believe that VR is even more fundamental, and that its impact could potentially be even greater, as we will see shortly. So the key elements have come together now, and the shape of the future of VR is emerging, but we're only at the start of that process. VR is already a unique, compelling experience, but it's obvious that it can and will improve hugely over the years to come in every respect, including resolution, field of view, tracking, mixed reality, audio, interaction, interface, applications, and content. Across the board, we're only at the start of a ramp that will last for decades. Human-oriented computing has been evolving for 40 years now, and VR, which has both greater potential and greater challenges, will surely evolve for much longer than that. And I have little doubt that before 40 years have passed, the daily lives of most people on this planet will include both VR and AR, which will eventually fuse into a single pair of glasses that can deliver AR, VR, mixed reality, anything on that spectrum. Right now, all that is in the future, waiting to be invented. And that is the opportunity of a lifetime that awaits you. Being there in the early days and being a part of something new is incredibly exciting. And it's also a great opportunity to have a big impact quickly. Before things settle down, everyone piles in. I've experienced this personally several times. So the first time was when I wrote video games for the PC in the early 80s. When it had just come out, it was barely powerful enough to support animation. I want to give you a context for how slow this was. An 8088 ran at 4.77 megahertz, but it took 4 clocks to fetch each byte, which meant that every instruction byte basically took almost a full microsecond. So if you were using, on average, 3-byte instructions, that meant that you could execute 1/3 of a million instructions a second. Real-time animation with 1/3 of a million instructions a second is an interesting challenge. So this is a screen from my first commercial game, Space Strike. I think we could agree that this probably wouldn't be a bestseller now. However, at the time, It was a miracle performance programming, and it made it into the top 20. Not the top 20 games, the top 20 PC apps. So when you get there early, all sorts of things can happen. And the most amazing part was that I wrote every bit of it. Code, animation, art, such as it was, sound, everything, by myself in 3 months. It was incredibly fun. I learned a huge amount in a very short time. Nowadays, expectations are much higher, and I could never have done or learned so much so quickly. Or consider, and in case you're curious, this slide is because we really couldn't find an appropriate Quake slide that really was available. So you can kind of ignore the slide, they just stuck it in there. Or consider when John Carmack and I worked on Quake. There were just the two of us to do all the architecture and coding, and we got to dive into everything from DSP trees to collision detection to scripting to client-server networking to prediction to performance to hidden surface removal, and we did it all from start to finish in less than 18 months. I've never had a better learning experience in my life or a more exciting time, and it had a broad impact. To this day, I often meet people who reminisce about how awesome it was deathmatching when Quake came out, or who thank me for helping to make their careers in the game industry possible. Just as important, the work on Quake led the way to many other interesting things over the years. In my case, it was a key step on the path to making VR happen. And actually, I'll throw in something else here interesting I think is pretty relevant to you guys. So when ARPA decided to make the first 4 nodes of the ARPANET, they went to the 4 locations, and they presented the plan. They said, in September of 1969, you are going to get these interface computers that will hook up to your computer and that will connect to each other through dedicated phone lines. And that will be the ARPANET, and so be ready for it. So they presented to the faculty and the grad students, and the grad students started talking with each other about what they were going to need to do, and while they were talking, they were thinking, I wonder what kind of protocols what they called the wise men back east, who ARPA had hired to design the protocols, would do. And so they started speculating, and they got together, and they talked about it. And after a couple of months, they kind of had a design, and they thought, well, these are interesting ideas. So we'd like to get feedback on it, even though it wasn't their job. So they thought, well, how do we do that? We'll put it out there. We'll give it a name. They said, we'll call it request for comments. So that's where RFCs came from. So they put out RFC 1 and waited for the backlash from those wise men back east, and there was no backlash. And there was no backlash from RFC 2 or RFC 3. And then there was a meeting at Bolt, Beranek, and Newman, who was making the interface computers. And BBN explained that here are the computers, here's how they'll hook up, and we are implementing the lowest level physical transport, actually copying the bits between the computers, but nothing else. And gradually what had dawned on these grad students was nobody had been hired to do the protocols. That it was just expected by ARPA that these would show up and they would work. So suddenly, they had until September 1969 to actually implement those protocols. And they did, they barely made it. But we're talking about John Postel, Steve Crocker, Vint Cerf. These are the people who are the gods of the internet, right? They basically made one of the most important technological creations ever. And it was just because they were there at the beginning, there was the opportunity and they seized it. You are positioned to have that kind of experience in an even bigger way today. Right now, there are all sorts of interesting questions to be answered. How should locomotion work in VR? What sort of rendering works best to create presence, especially given that it's clear that many of the techniques used for the last 25 years really don't work in VR? What's the interface that will do for VR what windows, menus, and dialogues have done in 2D? What will it take to make interacting with avatars as satisfying and convincing as interacting with real people? And how does all that co-evolve with advancements in hardware? Right now, you have as good a shot at being the person who answers these questions as anyone on the planet. Of course, that assumes that VR actually is going to be that important. Sure, it makes for great movies and novels, but is it really going to change the world, or is it just going to be the next 3D TV? Well, I'm not the person giving you an unbiased opinion on that. I think that's pretty clear. But it is very clear to me that VR is something special. In fact, it's something unprecedented in the history of technology. To understand why, we need to take a short detour into the minor matter of the nature of the reality we experience. Most likely, it's not news to you that the world is a complicated place. However, you probably don't realize just how complicated it is, or just how inadequate your senses are for the task of understanding it. In particular, trying to understand a 3D world using 2 2D imagers, 2 small sound receivers, and a bunch of mechanoreceptors is an impossible problem. Literally, it is an impossible problem, unless you make a lot of assumptions based on millions of years of evolution and a lifetime of experience, which is exactly what you do. You constantly take in the very sparse input from your senses, together with a huge set of priors in your current model of the state of the world, and you infer the new state. Another way to put it might be to say that you hallucinate the world around you based on the most probable assumptions. Although fortunately, that hallucination almost always matches the real state of the world, at least in the most important respects. So that's more than a little hard to believe at a gut level, right? You can hear it, but you don't really believe it. Given how solid our perception seems, so let's take a whirlwind look at some cases where the hallucination breaks because the assumptions aren't correct. Now, those of you who have seen my talks are probably pretty familiar with these.
Are you trying to advance your slides?
No, actually.
Oh.
I think it'll advance next time. If it doesn't, though, let me know. See the white tile under the desk and the black tiles just outside the desk? So these. Let's mask off everything else. They're both exactly the same shade of gray. But if one of them is in shadow in that shade of gray, it must be white. And if the other is in bright light and is that shade of gray, it must be black. Your visual system does that inference for you automatically, because in the real world, that assumption is almost always correct. So what you see is white and black rather than gray. Let's look at how we perceive form next. Take a moment, figure out which of the two tabletops is wider as measured in 2D. Just those blue areas, which one's wider and which is longer, assuming you rotated them to line up. Ready? They're exactly the same size. So do you think the shape morphed while it moved? I certainly did the first time I saw it, but they are indeed the same size. And in fact, here, I'll hand this around. In this, you will find this and this little piece punched out. You can do it for yourself. And even just looking at it in cardboard, you will still think that it's morphing while you're turning it. We live in a 3D world. And the 3D objects implied by the 2D shapes of the tables are quite different from each other. Your brain does that calculation automatically for you, making the assumptions that you're looking at a 3D world. That's wrong in the specific case of trying to compare 2D table sizes here, but in general, it allows you to function in a 3D world, which is where you happen to live. We also make assumptions about 3D structure and continuity. To me, this looks like a double-peaked roof. Interestingly, the reflection looks like a single-peaked roof. Let's see what they look like as the view angle changes. Bizarrely, now the roof is single-peaked and the reflection is double-peaked. Here's what's going on. Now that we see the true shape of the roof, let's look at this illusion again. The guesses our visual system made here about the roof line were not only perfectly reasonable, they were by far the most probable states of the world given the available data. They just happened to be wrong because the highly likely assumptions that they were based on were wrong in this particular case. Now let's look at a case involving motion, the Ames window. Of course, the straw isn't really going through the window. There are a number of cues on the window that imply a perspective that doesn't exist. So your visual system infers that the window is spinning backward for half of a full rotation. As a result, the straw seems to rotate right through the window. This doesn't match any reasonable model of reality, so you end up seeing something impossible. The next example also makes an incorrect inference, but it doesn't wind up with an impossible solution, just an incorrect one. Okay, that's just weird, right? Here's what's actually happening. Real objects, especially faces, tend to be convex. So your visual system assumes convexity in the absence of cues to the contrary. The only way to make that assumption work in this case is for the head to be moving in very odd ways, so that's exactly what you see. So what's interesting, when I say in the absence of evidence to the contrary, when I talk about your brain making an inference from all the data available, if you do this in the real world with both eyes, it absolutely doesn't work because you have stereo. But if you shut one eye, it goes back to doing this. right? So add more data, you'll make a better inference. But here's the best part with this one. Now you know what's happening, right? Try to see the dragon as it really is. I bet you can't do it. A little bit of conscious knowledge isn't going to undo a million years of evolution and a lifetime of looking at faces. So normally, about 10% of you can manage to hang on to that all the way through this. Who still sees it the right way?
What?
Wow, you guys are good. What did I say? Actually, what I find is if you get distracted while you're keeping that concentration, it will snap and you can't snap it back.
Yeah.
Okay,
Yeah.
finally, let's look at a multi-sensory illusion,
Yeah.
the McGurk effect, which is one of the best demonstrations I've seen of how we infer reality.
Bar, 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 bar.
Obviously, she's saying bar, bar, bar. Now let's watch a slightly different video and see what she says.
Bar, 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 bar.
Here we can clearly hear her saying far, 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 except that she isn't. The video shows her saying far. Her lips are moving in the correct way for far, but the audio track is still of her saying bar. It is the same audio track as it was in the first video. And yet, we clearly heard her saying far. The visual input is overriding the audio. So to make it crystal clear what's going on, let's look at this one more time. Once again, we'll have a soundtrack that says bar, but now we'll have a split screen with a face saying far on one side and a face saying bar on the other. As this plays, move your eyes back and forth from one side to the other and observe how what you hear changes.
Bar, 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 bar.
You're tracking my head, right?
And we're all turning in sync.
No, actually, we multi-view. You're each getting their own. So the fascinating thing there, though, isn't that you kind of thought, oh, I wonder if that's bar or bar. You just heard it, right? Even though you know the audio is only bar. You literally heard it. And that tells you what your reality is, right? You hear things because your brain inferred them, not because sound waves hit your eardrums. So, you're not a microphone. You're an inference machine that integrates all available data to construct the most likely model of the world. And this is an emphatic answer to the question, what is real? Okay, so all that was fun. What was the point? The point is that our experience of reality is a highly functional hallucination. The reality we experience is whatever our brain reconstructs it to be, based on those sparse inputs and our model of the world. In our personal realities, we all heard her say far and saw the dragon's head moving and thought the tabletops were different sizes, even though they weren't. I think it's fair to say that our experience of the world is an illusion that evolution has honed to be highly functional in terms of survival and reproduction. Which, finally, brings us back to virtual reality and why it's different from anything that's come before. VR is about experiencing information. Virtual worlds is real. And what we've just learned is that an experience is real to the extent it convinces your perceptual system and brain, because experiences are nothing more or less than whatever your mind infers from the data it receives. And our perceptual system does that inference automatically, regardless of what the conscious mind knows. What that means is that virtual reality, done right, truly is reality as far as the observer is concerned. The reality is artificial, but the experiences are genuine, deeply convincing, far below conscious level. So what does that mean? It's the difference between looking at this picture and actually leaning out over the top of the Eiffel Tower. No one ever stepped back involuntarily from looking at a picture, but I can tell you that's exactly what happens when I look over the edge of a long drop in VR. In fact, the first time that I stood on the edge of a pit in VR and looked over it, my knees just locked up. And I spent several minutes there waiting to see if this would wear off, but I'm wearing this thing on my head, I'm standing on a carpet, I just walked into a room, there's someone talking with me, and it didn't even look real. It was a square pit, and the walls were actually pages off Yahoo announcing that Facebook was about to go public. And the texture around it, the stone, was actually out of Doom. It was just one of those bright orange and yellow textures. So nothing realistic about the scene, except for the fact that there were these clean lines and good tracking, and it gave me this sense of parallax, and all kinds of systems kicked in. And when finally, at the end of several minutes, I said, okay, I'm going to make myself step off. In that split second before my foot came down, I just knew that I had made a huge mistake. And I don't mean I knew like I thought it. I just mean like all through my body was the utter certainty. I could visualize what was happening. It was just all there. And it was really as terrifying as if I had done it in the real world. If someone had moved the floor down an inch, probably I would have had a heart attack. Not 1 inch. So that's what I mean when I say the experience is genuine. So I'd spend more time trying to convince you, but since you're all taking a VR seminar, my guess is that you already believe in the power of VR. So let's talk about what it might mean to you personally. So VR is hard. Really, really incredibly hard. Driving the human perceptual system to create experiences is amazingly complex and not well understood at all. And there are deep unsolved problems everywhere you look, often with no clear path to a solution. And that is a great thing for you personally because it means that VR is a research and development goldmine, quite possibly one of the biggest ever. VR is opening up new frontiers in graphics, computer vision, audio, haptics, sensing, optics, displays, performance, and much more in ways that hasn't happened since Xerox PARC. If I were about to graduate with a computer science, engineering, physics, or math degree, I couldn't think of a more fertile area in which to find a meaty, worthwhile challenge than VR. So this slide gives you an idea of the breadth of the work going on in VR. I'll just give you a moment to look through this because it covers an amazing amount of ground. Next, I'd like to dive into just one part of one aspect of VR, photon delivery, to give you an idea of the depth of the challenges. So by photon delivery, I mean putting the right photons in the right places on the retina at the right times to create the desired visual experience. The current version of the Rift does this well enough to create good virtual experiences, but that can get much, much better, and all sorts of interesting challenges remain. So for starters, there's pixel density. To reach retinal resolution, we need 100 times as many pixels. There's field of view. We're at about 90 degrees. The full human field of view is up to 320, believe it or not. There's high dynamic range for both color and intensity. There's rendering, where we need to think about new ways to render scenes with tens of millions of pixels at 90 hertz. And one of the fascinating things about VR is that if you miss a frame, bad things happen, right? You can do warping and so forth, but you can't really get head motion right because you start getting occlusions and disocclusions. And it really is more of a real-time challenge than anything that's come along in a long time, more so than games. There's ergonomics. We need to be able to comfortably remain in VR for hours at a time. And finally, there's depth of field, which requires a little explanation and is also a good place to dive a bit deeper into VR research. So like a camera, the eye can only focus at one depth at any one time. Everything in the real world always appears to be in focus, but that's only because the lens of your eye changes shape to focus on whatever object you're looking at. For example, in this figure, the lens is stretched, so the parallel light coming from far objects is in focus. In the bottom figure, the lens is contracted, so it focuses light from close by. This changing of the lens shape to focus at different distances is called accommodation. And it happens automatically without you being aware of it when you look at the real world. Things are different with head-mounted displays. Because they use fixed lenses, they deliver all photons from the same focal distance, usually somewhere near infinity, no matter where in the scene the objects are located. In other words, where they are in terms of stereo disparity. In general, this works, although it has the odd side effect that everything in the scene is in focus at all times. It doesn't work perfectly, though. In the real world, accommodation and convergence, the degree to which the eyes pivot inward to get stereo alignment, are linked by the accommodation convergence reflex. As the eyes converge on an object, the lenses try to focus at the matching distance, and as the lenses focus on an object, the eyes try to converge at the same distance as well. So in this slide, you can see that the eyes have rotated inward to do stereo matching, and at the point of interest on the screen, and the lenses have changed shapes to focus at that point. So all four lines meet at the same place. Accommodation and convergence match, and that's the way it always is in the real world. Things are different in VR. Because the only valid focal distance is near infinity, accommodation can't change to match convergence at nearer distances. In the figure on the right, you can see that the eyes have rotated further inward to do stereo matching at the middle of dotted line here, but the lenses are still accommodated at the fixed focal distance of the screen. As anyone who's used a VR headset can tell you, and you probably all have used VR headsets, this actually works fine, but it may contribute to fatigue or discomfort for some people. So there's interesting research to be done about how to address it. One possible approach is multiplanar, which composites multiple displays at several different focal distances. So Kurt Akeley implemented that for his dissertation, and the results were promising. Unfortunately, His system was the size of a small file cabinet, which is not ideal for head mounting. A second approach would be to use a multi-lens array backed by dozens of different views to produce something approximating the full light field reaching the eye. And that would give you the correct focal depth for everything in the scene. So Doug Landman's one of our researchers now, but when he was at NVIDIA Research, he built a prototype that was a glasses-like system that generated a pretty good approximation of the full light field. The downside was that Doug's system required 50 times as many pixels as a normal display. And there aren't a whole lot of 100 megapixel head-mountable displays out there, let alone the 5 gigapixels that you would need to reach retinal resolution. Then there's holography, which holds the potential to generate exactly the right photons. The big problem here is figuring out how to get very wide field of view head-mounted holographic images of high quality to update in real time. Finally, there are varifocal displays where the plane of focus changes dynamically to provide the correct focal distance for the object of interest. And I'm going to look at this a little more closely because it gives a hint of how deep the psychophysics of VR go. The basis of varifocal is changing the focal plane as needed, and that's very definitely not trivial to do. But even once it's accomplished, for example, by moving the lenses relative to the display, tracking eyes so that you know where the convergence is, that's not the end of the story, because everything in the scene is still always in focus, just at the new focal depth. This is very different from the real world, where objects at different distances will be defocused, and therefore blurry to varying degrees. Now, you would think it would be a good thing to get rid of that blur and to be sharp everywhere. It seems like it's a defect of the eye that it's like a camera, but it turns out that, as usual, the brain uses all the data coming to it. And in this case, the data from that blur is quite important. So one of the things it tells you is when you're looking at something, how far away are the things that are not at that focal plane? And you know that. You don't know why you know it, but that's why. That's much more important than stereo disparity once you get away from the focal plane. The other thing is that as your eye accommodates, as the lens changes, how does it know where to stop? Well, it knows where to stop because the thing you want to look at is sharp, and everything else is not sharp in this gradient away from it. If you don't have that gradient, it's not clear that your lens is going to know as well where to stop. It may cause you to take longer to focus on things. You could become tired. So this can be addressed by blurring in software, but it can't be just any old blur. It has to closely approximate the defocus blur that happens in the real world. And that's challenging with respect both to getting the blur exactly right and doing it fast enough. But we're still not done. So chromatic aberration is how wavelengths of light come apart as they go through a refracting medium, like a prism. The chromatic aberration of the eye also varies with distance. And it turns out that's an important cue as well. And again, this could be synthesized in software, but this time it's trickier because the level of reliance on chromatic aberration as a focal cue varies between individuals. And it's not clear that using an average correction will work well across the population. And after chromatic aberration, there'll be something else to figure out. VR is like an onion. Fix one problem, like focal distance, and that'll expose a new one, like defocus blur. So the key point is that even one small area of photon delivery, which is only one part of the many challenges in VR in terms of interaction and tracking, has multiple deep and challenging research issues, spanning rendering, optics, engineering, programming, perceptual science, and more. And that's the way it is all across VR. It truly is that deep and that multidisciplinary. And make no mistake, this is not a hypothetical discussion in any way. At Oculus, we spent the last 2 years building both a highly capable product team and a highly multidisciplinary research team, and lots of other companies who you've heard from and will continue to hear from are fielding strong efforts in both VR and AR. The future is being built right now in real time. So when you listen to the veterans of the early days of human-oriented computing, what always comes through is a deep feeling of satisfaction of what they accomplished, and an overwhelming sense of how exciting it was to have been there and done that as things really started to happen. The reason I said at the start of this talk that you are among the most fortunate people on the face of the earth is that that same experience is yours for the taking. All you have to do is jump in and work hard, and you'll find yourself building the future. Pretty hard to beat that. Thanks.